the third of 4 videos on linear regression. If you've not yet watched the first 2 videos, please go back and do so before you watch this video. So in the previous video, we discussed how to calculate the slope and the y-intercept of our linear regression equation. And another one of our goals is, once we have that equation, to actually plot and construct that respective best fit line. Now, we're not going to go through the details of doing that in class because many of your prerequisites for this class required you to be able to plot a line based on the slope and the y-intercept, and also there's a variety of different software tools that you can use to do this. So this video is going to focus on our third and our fourth goals for linear regression. And so this is going to be to make predictions using our regression model, and then also to estimate how much variation y is explained by x. So if we go back to our data set that we used from the last video, say that we're looking at salinity versus total length of Gulf Menhaden or Atlantic Menhaden. And we can go through and we have our data, we can plot our data, we can plot a best fit line, and we can calculate the slope and the y-intercept. So we have the equation of our best fit line. Now, in certain circumstances, we might be interested in making predictions outside of the data ranges in which we've collected. So we noticed that we didn't collect any data between about 8 parts per thousand and 12 parts per thousand, so maybe we were interested there. We also didn't collect any data outside of 15 parts per thousand. So maybe this is the area that we're interested in, because we know that menhaden move between lower salinities and higher salinities, and we want to know, as they move into higher salinities, what is the size of these fish likely to be. So we can potentially use our regression model in which to make these predictions, and then afterwards we can test those predictions with actual data that we go out and collect to see how good our regression model fits the data once we go beyond the initial sampling range. So our goal here is going to be to use our regression equation in which to make predictions about salinities that are higher than those that are in the initial data set. So if we look here, our salinity values on the left here are now higher than that maximum value, and we're going to use our regression equation to predict what the length of these fish should be based on the data that we've already collected. So for each one of our respective salinities, we're going to input the value of that into x in which to predict our y value, so our y hat value. So for a salinity of 17, when we put that into our equation, we should have a predicted length of about 24 centimeters. And then if we put 19 into our respective equation, we should get a predicted length of about 27. 21 for salinity, put that into x, our predicted length is going to be 30, and we can go through this and do this for all of our potential salinities that our fish may reside in. Now, something important here to note is that our predictions are simply that, they're predictions. They're not actual data. So before we can actually conclude that these are the trends, we need to go out and collect data from these different salinities. And we may find that our actual data are different than our predictions. And so what we have here when we plot our best fit line is that we can see that these higher salinities aren't really predicted particularly well for the length of the fish. And we need to think about things a little bit deeper when our predictions do or do not fit our regression model. When we start to extrapolate, we start to move beyond the values of our initial data set. Here we know that animals, including fish, oftentimes reach relatively max length based on their life history. So these fish only reach 30 to 40 centimeters in length during their lifespan. And so what we see here is that many of our predictions for higher salinities are quite high. And the reason that they don't fit our actual data is because the fish don't grow that size. But what this model and what this method does is it allows us to make predictions and then test those predictions and then make adjustments to our respective model, and to continue to do this through the scientific method. Okay, so our last goal for linear regression that we're going to talk about in this video is estimating how much variation we have in our dependent variable based on x, our independent variable, and then in the next video we're going to talk about its significance. So if we go back to correlation in the previous topic, we know that we can calculate the correlation coefficient to determine how well two variables are related, how strong their relationship is. And the closer they are to either 1 or -1, the stronger the correlation is. And depending on if the correlation coefficient is positive or negative, it indicates the direction of that relationship. When we talked about correlation coefficients, we also talked about the coefficient of determination. And this is going to be what we're going to use for linear regression to describe how well the independent factor explains the dependent factor. So how much of the variability in our dependent factor rather is explained by that independent factor. And our r-squared values are going to range from 0 to 1. Similar to our correlation coefficient, the higher these r-squared values are, the tighter the data is going to fit to our regression model, to that straight line. And when we move forward after this video, we're going to then determine if this model is significant based on the data using information from this r-squared value. So how do we go about calculating r-squared? Well, in order to do so, we need to calculate several different sum of square terms. So we need to calculate the total sum of squares for our respective data. We need to calculate the residual sum of squares of our data, and this is equivalent to when we're thinking about the within groups sum of squares for ANOVA. And then we also need to calculate the regression sum of squares. So if we know 2 of the 3 of these, we can calculate the other, just like with ANOVA. Or for this regression sum of squares, we can use this formula. So what we see here is that the total sum of squares is our respective data minus the mean squared, and then taking the summation of that. Our sum of squares of the error, or the residual sum of squares, is the data, the y values, minus the predicted y values squared, and then taking the sum of that. And then our regression sum of squares is a little bit more complicated, but the formula is not to that which we cannot calculate. And then when we calculate this r-squared value, we're then going to use that to provide the reader with the information on how well our relationship explains the data. So how well does X do in explaining Y? So we're going to go through an example in Excel, and we're going to start from the beginning calculating the slope and the y-intercept, and then we're going to go through and calculate these sum of squares and eventually this r-squared value. Okay, so we're going to go through an example in which we're going to calculate the r-squared value for a respective data set. But before we do so, we're going to go through and calculate out the slope and the y-intercept in which to get some extra practice. So we have our data set here, and we're interested in how body weight affects the amount of mass in the stomach a particular animal. So essentially how much food an animal eats, and we might predict that as an animal gets bigger, it's going to be eating more food. So again, another good important first step, plotting our data, seeing if this makes sense based on our data set. It does look like that is the case, and in Excel and in other programs you can generate both the regression equation as well as the r-squared value. Now, for the assessments in this particular course, you're going to need to show each one of the steps in the calculations that you're making. So it won't be acceptable for you to just do this through Excel. But this is a much faster way to go about it, not through hand, but we want to get an understanding of how this is calculated. So let's go through some practice here. We can go through and calculate the slope of our respective regression line, again using both of the formulas, so getting comfortable using both of these formulas. So for this particular formula, we need the means of both body weight and stomach contents mass, so our x's and our y's, so that's going to be our first step. We then need to calculate differences between our respective data and those means, so we can go through and we can calculate those, again using formulas or doing it by hand. We're then going to need to calculate our denominator and our numerators, and for this particular purpose, our denominator, we need to take the squared values of those x values minus the means. And then for our numerators, we need to multiply the difference between the data and the means for our x's and for our y's. So we can go through and we can calculate those again. In the Excel spreadsheet, we have our formulas here, so you'll be able to check yourself on each one of your calculations. And then we need to take the summation of these and then simply divide the numerator by the denominator. So that gives us our respective slope. And again, you can go back and you can check your formula here based on generating this from Excel, and we get the same value. If you feel more comfortable using the other formula, we can go ahead and do so. We'll go through that so we can get some extra practice. So we need to calculate not only our summations, but we need to calculate our x squareds and our x times y's. And so we can go through and do that. And then we need to take the summations respectively. So the summation of xy, summation of x, summation of y, summation of x squared. And then following orders of operations, we need the summation of x and then squaring it. So we can go through and take the summations of each one of our respective columns, and then we can calculate out the numerator and the denominator. Again, noting that small n is the number of data pairs. So in this particular instance, we've got 10 different data pairs, so that's what our value for n is going to be. So we can calculate our numerator, and what you'll notice here, we've got our formula here, and then we can go through and calculate out the denominator. We're going through this quickly because this should be review for you, and we'll be going through examples in class. So we can get our slope. Again, this slope is the same as the previous slope, so it doesn't matter which formula you use, it just matters that you can effectively use at least one of them, if not both. Next, we need to calculate the y-intercept. So we're going to use our slope of 0.13384 for b here, and then we're going to use our means of y and our means of x. So it's just a matter of inputting those values into the respective formula. So here at the bottom, we have our regression equation. This is our y-intercept, this is our slope. Put this into our respective formula structure. Now, in order to calculate r squared, we need to calculate some sum of squares. So the first one that we need to calculate is our total sum of squares, SST. So we need to take our y values, we need to subtract the means, and then square each of those, and then after that take the summation. So the first thing we're going to need to do is we're going to need to square take those values. So we can go through and we can take our respective y values for stomach contents, we can subtract the mean, and then we can square each one of those values, again following orders of operations. After we do this, we can then take the summation of those values. Again, if we take the summation before we square it, the value is not going to be correct. So we have our total sum of squares. The next step is going to be to calculate our residual sum of squares, or the sum of squares of the error. So for this, we need to take our y values again, and then we need to subtract our predicted y values based on our regression formula here. Once we have those differences, we need to square them and then take the summation. So in order to do this, first thing we need to do is calculate our predicted values. So we can use our regression formula here in which to do so. So we've got our y-intercept here of 0.635903, and then plus our slope times our respective x value. Again, making sure that we're following the formula here. This way we can then calculate what we're predicting on y based on x. Again, let me say that again. The y hat value, these predicted values, are what we're predicting for y based on the value of x using our regression formula here. Once we go through and calculate out our predicted values, we then need to take the difference between our actual y data values and those predicted values. We can go through and calculate those. Now what you'll notice here is we have some values that are positive and some that are negative. If we go back to our regression line and our formula, we notice, well, there's some values that are above the line and some that are below. So we're in good shape here. Now a good double check for us to make is that the summation of our y values minus the predicted values should be equal to or very close to 0. Meaning that we've got an even distribution of data above and below the best fit line. So you can take the summation of that column and check to make sure. So this is 3.1 to the negative 15th. If your value is not close to 0, it means that you've made a miscalculation somewhere, and this could be that your regression formula is off, or the calculations that you made for y hat are off, or the differences are off. After we've done this, we then need to square each one of these values. So we can do that, and then we need to take the summation. This is going to be our residual sum of squares. Once we have our total sum of squares and our residual sum of squares, we can then put them into the formula here. Now noting that in order to calculate r squared, it's 1 minus the ratio of the residual sum of squares to the total sum of squares. This 1 minus is important. Once we do that, we can calculate our r squared value, and that's going to indicate to us how much of the variability in y is attributed to x. Now, let's say that you don't want to calculate out the residual sum of squares. You're more interested in using this other part of the formula in which we're calculating the regression sum of squares. Okay, great, we can do that. Well, in order to do so, we still need to calculate the total sum of squares, which we just did, but then we're going to use this new formula to calculate the residual sum of squares. So we're going to use the following formula here with summations of x, summations of y, summations of xy's, and then using the slope. Again, n is indicating the number of data pairs, not the total number of data points. So we can go through and we can calculate out our regression sum of squares using the information that we have, and then we can go through and we can calculate our r squared value. Again, it's the same, it doesn't matter which formula you use, and as long as you know two of the sum of squares, you can calculate the other. So we have an r squared value of approximately 0.5. And so if we remember back to the correlation lectures, this means that about 50% of the variance in y is based on x. So when we know the values of x, this means that we reduce our uncertainty in y by 50%. So it seems that x is important, but we also know that 50% of the variability in y is not related to x. And so we then begin to ask, well, is this relationship and is our model significant? Is it of value to have this model when we're making predictions about y or not? And this is what we're going to talk about in the next video. But before we do so, I'd suggest checking out section 14.6 in your text. So again, the fourth and final video for linear regression is going to be determining the significance of our respective regression models.